Hey guys, and welcome back to the Fundamental Theorem. In this video, I want to go over some basics about sines, S-I-G-N. I should be very clear, not S-I-N-E. And I know at times it can get a bit confusing because we're dealing with trigonometry after all, aren't we? But yeah, if you look at trigonometry in the conventional right angle triangle sense that I'm guessing you're all accustomed to viewing it in, well, you actually find it quite hard to think of sines of angles actually being negative, right? It seems ridiculous that sines or cosines could have negative values. I mean, what does it mean to say that the ratio of the side opposite to the angle to the hypotenuse is negative? What does that even mean? Well, the key to understanding this actually lies in what we discussed last video, the relationship between circles, triangles, and trigonometry. And before proceeding, I just want to briefly recap what we did last time. Well, last time we looked at expressing the location of a point in two-dimensional space in terms of two very different quantities from the ones we're used to expressing it in, right? We usually express it in terms of x and y, the distance moved horizontally and the distance moved vertically in order to reach that point. Last time we looked at a perfectly valid representation of a point, of the location of a point in terms of how far away it lies from the origin and the angle to the positive x-axis in which one would need to walk in order to reach that point, right? And well, it's actually important to note the significance of this so-called polar coordinate system and how it ties in with circles. The thing is, the basis of the polar coordinate system, rather the most elementary quantity in which the polar coordinate system deals, is actually the circle. And the reason for that is that the distance from the origin, this quantity r, essentially represents the set of all points lying a certain distance from the origin, i.e., a circle, right? And the reason why this angle theta is so important is because it actually denotes a certain arc on that circle, right? And well, again, there's a reason why I mentioned arcs specifically. It has to do with this measure of angles known as radians, which is, well, a little bit different from the more conventional measure we're used to, right? Which is degrees. So, for example, well, the specific relationship between degrees and radians is that pi radians equals to 180 degrees. And well, personally speaking, I think the reason why the radian measure is so great is because, well, it accomplishes two things, right? Number one, it scales down the degree scale because if you were to graph y is equal to sine x, a graph that we'll be exploring in more detail next video, by the way. Uh, anyway, if you were to graph something like y is equal to sine x, if x were in degrees, then, well, the graph would just look really huge, right? The reason being, you would have to travel 180 units along the x-axis to complete a semicircle, right? And that's pretty far. So the radian measure conveniently sizes all of that down into more manageable numbers. And again, the reason why we have pi into the mix, well, I think it just makes calculations a whole lot easier, right? I mean, this is the way I looked at radians when I was first introduced to it. And the reason for that is if you're looking at areas of sectors or the lengths of arcs as fractions of the total area of the circle, or the perimeter of the circle, that is the circumference, then, well, pi pops up in the formulae for both the perimeter and the area, right? And that has to do with the definition of pi. Perhaps I'll make a video about that some other time. But for the moment, I'm expecting that you're familiar with the fact that the perimeter or circumference of a circle is equal to 2 pi r, where r is the radius and pi is, pi. And the area is pi r squared. And well, why we have pi in this radian measure is that if we look at the angle formed by that particular arc or that particular sector as a fraction of the total, we in fact wind up with the quantity pi in the denominator. And when you multiply that by pi r squared or 2 pi r, the pi's cancel out very nicely. I know that was quite a bit to take in, but that's just a little bit on the side. I mean, there are plenty of great resources online about the radian measure and about pi and all of that. But anyway, moving on. For this video, I want to take a quick detour and I want to go over some pretty basic concepts. Now, you're probably familiar with all of this, but I just want to go over it once again. So the thing is, uh, whenever you have two axes dividing two-dimensional space, we notice that they divide the space into four distinct regions, which we call quadrants, right? And conventionally, we take points lying to the right of the vertical axis to have a positive x coordinate. We take points lying to the left of the vertical axis to have a negative x coordinate. Points lying above the horizontal axis to have a positive y coordinate, and points lying below the horizontal axis to have a negative y coordinate, right? We also have the point of intersection of these two axes to be the point 0, comma 0, also known as the origin. And I mean, the thing is, when you have these axes that extend infinitely in all directions, well, you need a point of reference. Without taking this point of intersection as a point of reference, if you chose something else, it would be very difficult to identify the location of a point with respect to that point of reference. We need to have an international standard, and the universal standard, as this so-called point of reference, is the origin. This is just by pure convention. But yeah, uh, if we bring back our little friend, we notice that, okay, this method of identifying the location of a point in terms of its distance from the origin and the angle, right? That should be valid no matter which quadrant the point lies in. And this seems fairly obvious because we know that the angle merely represents a location on that circumference. I mean, this just makes natural sense. And in the previous video, we looked at how we could convert this into our, the more familiar rectangular coordinate system, right? Where we use an x and a y coordinate, where we use the distance moved horizontally and the distance moved vertically from, lo and behold, that point of reference, the origin, right? And well, it therefore seems natural to infer that since in the second quadrant, um, you know, the x coordinate is negative, the value r cosine theta should also be negative, right? And well, okay, there are two quantities that are involved here. One is r, the other is theta. So one of them has to be negative, right? Either r or theta, to be more precise, cosine theta, right? Well, r is just the radius of the circle. It acts merely as a scale factor. I mean, it doesn't even have a bearing on which quadrant the point lies in, right? Look at it. If we reduce the value of r, we notice that the circle seems to shrink in size. If we increase it, the circle gets bigger. And if you pay close attention to the value theta, theta remains unchanged, as does the quadrant in which that particular point lies. So we can discount r as the source of that negative sign. Well, that leaves us with theta, or to be more precise, cosine theta. And therefore, we see that by convention, cosine theta is considered to be negative in the second quadrant for all angles theta that put that particular point in the second quadrant, to be more precise and to just iron it out. Well, okay, let's see this in action for ourselves. Okay, we know that these two refer to cosine and sine theta respectively, right? Now, in the second quadrant, notice what happens to the y and the x coordinates, right? Going by our conventional definition that cosine of an angle equals to the ratio between the side adjacent to it and the hypotenuse, right? Going all the way back to SOHCAHTOA and what have we. Well, we notice that in the second quadrant, the x coordinate is negative, which means the side, quote unquote, adjacent to our angle theta has a negative value, which means the ratio of that to r, again, r is just a positive value, right? It doesn't make sense for us to have a negative r. Well, that would actually amount to flipping the circle on its head, but that's a discussion for another day. Well, as we can see, the ratio of the horizontal component to this hypotenuse is negative, which means cosine is negative. We also notice that the point remains above the horizontal axis, which means that the vertical coordinate or the y coordinate remains positive. As a result, we can conclude that sine theta remains positive in second quadrant. And we can visualize this for the third quadrant as well. We see that both x and y become negative, therefore both cosine and sine are negative. In the fourth quadrant, we notice that, well, sine remains negative, but cosine becomes positive. This is because we're moving across the vertical axis again, right? And as we know, moving across the vertical axis has the effect of multiplying um, our x component by the value -1. Right? We can see this just by the convention of taking values to the right as positive and values to the left as negative. I mean, at least the x coordinates of these points. Well, okay, we see that this just repeats in a cyclical fashion, right? And in fact, this cyclical nature gives the functions cosine and sine uh, the name periodic functions. This is because they happen to repeat in an identical manner over certain given periods. And well, okay, the natural question then is, what are the periods of sine and cosine? Well, okay, let's look at this axiomatically. We know that the actual values of sine and cosine remain unchanged. How do we know this? Well, okay, think about it. We're looking at points that lie on a circle, right? And we know that the origin is the center of the circle, which means we know that the axes essentially divide that circle into four identical paths, right? Given that these four paths are exactly identical to each other, it only makes sense that the sine and the cosine components have exactly the same magnitude. They have the exact same value. Aside from the positive and the negative, they are the exact same value in all four quadrants. Well, okay, what else do we know? We know that only the signs change based on the quadrant in which the angle lies. Again, we just saw this, right? This is axiomatic. If we combine these two facts, it follows only naturally that if we know over which interval these signs reset, we automatically know over what interval that function is so-called periodic, right? I mean, this applies to sine and cosine, right? This seems very natural. And okay, let's examine sine first. We know that it's positive in the first quadrant, positive in the second, negative in the third, and negative in the fourth. And then we know that this resets, right? And well, that means that the period of the sine function is all four quadrants or 360 degrees, right? And if we go back to what I said at the beginning of the video, that the relationship between radians and degrees is such that pi radians equals to 180 degrees, it follows that 360 degrees is equal to 2 pi radians, which means the period of the sine function, as you will find it commonly expressed in textbooks and videos, what have you, is 2 pi. Okay. Uh, Oh, I should probably mention, by the way, generally when we're referring to values in radians, it suffices to leave them in terms of pi. We don't normally mention that they are in radians explicitly. It's more or less understood. But yeah, that's just convention again. Okay, if we move on to cosine, we notice that the pattern of positive, negative, negative, and positive again resets after exactly all four quadrants, which means the period of the cosine function is again 360 degrees or 2 pi radians, right? Okay, now let's look at an interesting quantity. Let us consider the ratio between this sine and cosine, or this x and y. Well, okay, let's look at some things that we already know. We know that dividing a positive value by a positive value has the exact same effect as dividing a negative value by a negative value. In both cases, we get a positive value as the answer, right? Likewise, if we divide a positive and a negative value or a negative and a positive value, we get a negative answer, right? In other words, if we divide like signs, we get positive. If we divide unlike signs, we get negative, which means, in some sense, ignoring the magnitude, but focusing just on the sign, positive or negative, of this ratio, what it's telling us is whether or not sine and cosine have the exact same sign, right? again, like I said, it can be a bit of a mouthful. So if you're following, then you should know that when I say sign here, positive or negative, I'm talking about SIGN and not SINE. But yeah. Um, okay, so let's look at the values, rather the signs that this ratio can take. In the first quadrant, we can see that it's positive. This is evident. In the second, negative. In the third, positive. And in the fourth, negative. Well, this ratio actually has a very special name. It's known as the tangent function. And again, the name tangent has to do with the way in which it is formally defined. And well, many a time you find that these formal definitions are a bit pedantic and overtly specific. But I mean, they need to be that way in order for the definition to have absolute clarity, right? And again, there are plenty of resources online where you can see exactly how the sine, cosine, and tangent functions are, well, formally defined. Yeah. Um, okay, that's it for this video. Thanks for watching, and please do like and subscribe. Uh, if you're interested in more videos about trigonometry, I have left a link to this playlist in the description. So do check it out. Thanks for watching, and I hope to see you soon.